This presentation shows the method of selection and design of bioclimatic strategies for solar control and ventilation that have been or will be incorporated in the case studies of the LIFE-myBUILDINGisGREEN project. Although the project integrates more strategies such as green roofs, interior living walls, or draining floors, the methodology used for the dimensioning of the contemplated strategies involves a specific stage and tools, understandable to the non-specialist user. This video tries to bring the project to the viewer who has concerns and interest in this topic. The objective of the implementation of bioclimatic strategies is to improve indoor temperature and reduce the energy demand of HVAC systems in buildings. In order to improve the energy efficiency of buildings and their indoor thermal conditions, bioclimatic strategies that are most likely to succeed should be established. Although this constructive technique tends towards the reduction of temperatures in the summer season, it should be avoided that its implementation generates penalties in the winter season. This requires prior studies to define appropriate techniques for each case. In the project My Building is Green, a study has been carried out to evaluate the aptitude of different nature-based solutions that theoretically have the capacity to rehabilitate the case studies. Its methodology includes the analysis of historical climate records of each region through Climate Consultant 6.1. A software where the following climatic variables are characterized and represented graphically: temperature, relative humidity, solar radiation, natural lighting, wind speed, and direction. With this tool, psychrometric diagrams were created using hourly data, mainly of dry bulb temperature and relative and absolute humidity, to delimit the comfort zone and determine the number of hours in which the inhabitant is inside or outside his comfort zone. The position of the points in the diagram also indicates what kind of strategy can be used to reposition the same within the comfort area. The story pays special attention to appropriate summer strategies. Taking the climate into account is a fundamental part of the project. As an example, implementing evaporative cooling in Évora and Badajoz will have good results because they are low and very low humidity areas. On the contrary, in Porto being a wet area, this strategy will be counterproductive. In the project, the strategies identified by the program as best suited are different in all three cases. However, it can be observed that the shading of openings, the control of internal gains, and ventilation, gross or night, are recommendations present in all cases. With regard to the shading of the openings, a solar incidence study has been carried out for the correct design. From it are obtained the angles of impact of the sun rays and the south, east, and west orientations to define the dimension of the parasols. For the correct adaptation of these elements to the buildings, their geometry and positioning have been adapted to each case, considering factors such as the thickness of the wall, the existing protection elements, precise orientations, and other parts related to openings. This study intends to dimension the parasols appropriately so that they reduce the solar incidence in summer, but at the same time allow it in winter. The daily solar part in the Porto and Badajoz region has been described through cylindrical projection solar charts. Given the similarity of the solar incidence between Badajoz and Évora, the results of the first region are valid for the second. In order to determine the solar incidence to be avoided in summer season by means of horizontal sunshades, protection angle mask has been superimposed on the solar charts of the south, east, and west facing facades. Two diagrams are obtained that correspond to the periods from June to December and from December to June. In each solar chart, 7 curves are shown, one for each month. The horizontal axes show the angle at which the sun rises and sets, while the vertical axes show the solar height. Within the chart, each hour is traced, and it is identified if the temperature in that period is in a comfortable state. For example, the results of the calculation showed that in Porto, the angle of solar incidence is 55 degrees at 12 o'clock. With this result, the horizontal parasols could be sized. However, in the coldest season, sizing the parasols with an angle of 70 degrees would allow solar capture in winter. In addition, on the east and west facing facades, horizontal protection are not effective due to the sun's trajectory, so the use of vertical elements has been considered. Taking this into account, it is possible to choose the use variable sun shading devices, which obtain the benefits of maximum sunblock in summer and minimal obstruction in winter. This dynamic protection can be provided by vegetation, using plants that lose their leaves in winter and keep them in summer. Once the solar protections have been dimensioned, a study has been carried out that contemplates the solar trajectory and its incidence inside the buildings. In the analysis, different scenarios are proposed that contemplate the use of horizontal element, vertical or both, of fixed or dynamic protection, and of vertical parasols rotated at 90 or 45 degrees. It is considered important that the simulated day is close to the solstices and that it is a day with little cloudiness and a lot of solar radiation. To search for this period, the climatic simulation data were consulted. From the results, the solar energy that affects the openings is considered primarily to evaluate the protection capacity offered by the parasols according to their width and rotation. For example, according to the results in Badajoz, it is recommended that in winter the horizontal parasols do not have a width less than 0.5 meters to avoid the increase in demand for heating. In summer, the horizontal sunshades with a minimum width of 2 meters in combination with the vertical devices would minimize the sun rays during the first and last hour of the day on the east and west facades respectively. The greater the inclination of the vertical parasols with respect to the plane of the same one, the greater sun protection of these facades in the summer season. The use of vegetable elements and their dynamic behavior solve the requirements derived from the analysis. Through the vegetation, a changing shading can be obtained that offers the required dimension both in summer and winter, even avoiding the rotation of the vertical elements. To correctly design the ventilation openings of the building, different models of natural ventilation have been used. These methods are published by organizations such as the American Society of Engineers of Heating, Cooling, and Air Conditioning, or the Technical Building Code of Spain. This calculation takes into account, among other things, the wind speed and direction, the required airflow per person, the interior temperature, and the dimensions of the opening. Cross ventilation in a room is generated when there are two or more openings to the outside located at a similar height on the adjacent or opposite walls that make up said space. This type of natural ventilation has been shown to have benefits in terms of reducing pollutants and temperatures. Therefore, it has been considered an ideal strategy for the project, since it can refresh the environment and adapts to the traditional geometry of the classrooms. Previously, the CSIC has shown the benefits of different natural ventilation configurations in a conventional classroom. door and windows closed, door open and windows closed, door and windows of the same axis open and windows of the parallel axis closed, and finally door and windows of the parallel axis open and windows of the door axis closed. The last option is the one that has presented the best results in terms of ventilation efficiency. Air quality has improved by reducing CO2 by about 50%. Cross-ventilation strategies show promise in removing pollutants from the air and providing fresh air. However, it has been necessary to study the advantages of this type of ventilation in terms of thermal comfort. Using the OptiVent 2.1 software, two hypothetical scenarios of a standard classroom have been compared. In the first, the window remains open and the door closed, while in the second case, both elements are open. Opening the door reduces the total heat generated by 3% and produces an airflow 0.84 cubic meters per second higher than case 1. Despite the previous results, when delimiting the adaptive comfort zone in accordance with the ASHRAE 55-2013 standard, it has been possible to observe that, of the cases analyzed, only when the door is closed the room temperature is in the comfort zone. When opening the window and the door, the temperature falls below the comfort limits. Therefore, more in-depth studies are necessary to be able to incorporate all the bioclimatic strategies with an adequate configuration. Finally, a study has been carried out to determine the effectiveness of some of the techniques incorporated into the project, among which are plant parasols and natural ventilation. Through a computational model, different scenarios have been evaluated which, in addition to the aforementioned techniques, include other solutions with vegetation, green facades and roofs, and new wooded areas. To calibrate the models, the temperature, relative humidity, barometric pressure, and CO2 levels of the study cases have been monitored in their non-renovated state. The aforementioned strategies have been added to the computational model and simulations have been carried out for each of the scenarios. The results in the warm season show the progressive reduction of indoor temperatures and energy use with each strategy that is added. These figures show that the selected strategies have the potential to meet the objectives of the LIFE-myBUILDINGisGREEN project of reducing 5 degrees centigrades the indoor temperature and 50% the energy demand for refrigeration. The results in the warm season show the progressive reduction of indoor temperatures and energy use with each strategy that is added. These figures show that the selected strategies have the potential to meet the objectives of the LIFE-myBUILDINGisGREEN project of reducing 5 degrees centigrades the indoor temperature and 50% the energy demand for refrigeration.
In collaboration with the LIFE program of the European Union.